Example 2. A rectangle is inscribed under one arc of the sine curve. What is the largest area of the rectangle and what are the dimensions? So we want to determine what the length and the width are of the rectangle to give us the largest area if we're under one arc of the sine of x curve. So step 1 is to understand the problem. So we're understanding the problem by determining the largest area of the rectangle under the sine curve. So to really understand this, it's really going to help to go ahead and just draw sine of x. So we know that sine of x looks like this. There's sine of x. And we know that this is 0, this is pi, and this is 2 pi. And this is pi over 2, and 3 pi over 2. Where we're going to be focusing in is on this area right here. One arc of it. So I'm going to draw that just a little bit zoomed in. Where this is 1, and here we go. It's a little bit off. I don't like that one. Good enough. I'm just going to change the y value. There's 1. So this is pi over 2. This is pi. And what we want to do then is to find the value that makes this rectangle as large as possible. So we know that we'll call this value x. So then if this is pi right here, then this value right here is pi minus x, because it's the whole distance minus the same. So this length is the same as this length. So if I were to label this coordinate, it would be x comma f of x, but f of x is sine of x. Then this coordinate is pi minus x and sine of x. Okay? So if we break down our rectangle then, if here's our rectangle, we know that this distance right here is sine of x, and then this distance is pi minus x minus x. Because it's this whole, it's what it is this rectangle distance is this whole distance minus this small yellow piece. So it gives me pi minus 2x. So what we want to do is we want to maximize that. First of all, let's talk about our domain. Well, we know the domain just by looking at the graph. Is going to be 0 to pi. So now let's talk about the area of a rectangle. We know that the area of a rectangle is equal to length times width, where in our case, our length is sine of x, and our width is pi minus 2x. So what we want to do here then is determine the maximum. So we take the derivative. To determine a max, you take the derivative. So we get that the area is equal to sine of x times pi minus 2x. And there's two ways to do this. You can distribute or just use the product rule. I'm going to go ahead and just use the product rule. So d dx to both sides. And you get 0 is equal to cosine of x times pi minus 2x plus sine of x times negative 2. So you get 0 is equal to cosine of x pi minus 2x minus 2 sine of x. Now if you really want to, you can solve that by hand. However, it's a little tricky. So what I recommend to do is just plug that into your calculator and then find the zeros. So let's do this right now together. So what we want to do is, in our calculator, type in cosine of x, pi minus 2x, minus 2 sine of x. So you put that in your calculator, and then you hit graph. And you should get something like this. If your graph does not look like this, go ahead and change the window. So I'm going to change my window back to standard. And it's going to look like that. Notice that I think I added a domain restriction. Yeah. So here at the end I added that x has to be greater than 0 and x has to be less than pi. So now it's stuck like that. So I'm going to go zoom in. And I'm just going to scroll over till somewhere in the middle. So I'm about right here. Push enter. And it'll make it a little larger. Now what you need to do is you need to calculate the zeros. So to do that, we're going to go ahead and push second calc, zeros, and it's going to ask for 2 points, a left bound and a right bound. So I choose this as my left bound, this is my right bound, and we take a guess. So it tells me that I have an x coordinate of 0.710. So that's right here. This is x equals 0.710. That's close enough. And here we're going to do it again. Second calc for the 0. Here's my left bound. And then over here, there's my right bound, and I'm guessing that it's about right there. So this gives me 2.43. Okay, so we have our endpoints, which are x equals 0 and x equals pi. And we have our critical points, which are x equals 0.710 and x equals 2.43. So we're going to go ahead and plug these all into our area formula in order to find which one has the largest area. Because we're only in the terms of x, we don't actually need to solve for the second y value. If you wanted to, you could. So we get the area is equal to sine of 0 minus pi minus 2 times 0. I'm sorry, it's being multiplied. So we know sine of 0 is 0. This is going to be pi. Well, look at that. The area is 0. That doesn't work. It doesn't make any sense. So then we have area equals sine of pi times pi minus 2 pi. And you get, again, 0 times a negative pi, which gives you 0. Probably not right. So let's try our critical points. X equals 0.710. So area is sine of 0.710 times pi minus 2 times 0.710. And this is going to be equal to, and make sure that your calculator is in radians. If it's not, you'll have a problem. So here we're going to push sine 0.710 times pi minus 2 times 0.710. And we get 1.122. 1.122. Let's try the last one. X equals 2.43. Area equals sine of 2.43 pi minus 2 times 2.43. And we get that the area is equal to negative 1.22. So, in fact, this number 1.22 is larger than 1.122. However, this is negative. So it doesn't work because the area can't be negative. So ding, 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 here's our winner. Now for the summary. You have to answer our questions like this. If it was a multiple choice, you don't have to. However, I'm trying to get you ready for the FRQ. So here we go. The largest area of the rectangle inscribed under the sine curve is 1.122 units squared. So we don't know if it's feet, millimeters, we don't know. When x is equal to 0.710. Now we need to state the dimensions. The dimensions are, and it really doesn't matter which one you put in first. We never actually evaluated them, so we need to figure those out. Pi minus 2x, which is pi minus 2 times 0.710, which is equal to 1.721 by, well, sine of x, which is sine of 0.71, which is 0.65. And there's our answer. So we have the largest rectangle, which has an area of 1.122 with dimensions of 1.71 by 0.65. And there you go. That's how you do that. So what now I want you to do is try this one on your own. Determine the dimensions of a rectangle that has the largest area that is inscribed underneath the curve x squared plus 1. So go ahead on your own right now and try that out. Alright, now that you have an area and dimensions, let's work it out. First things first, I always draw a picture. So let's draw a picture. We know that x squared plus 1 is going to look like this. Very roughly at least. And we just need two generic points that are going to give us a rectangle. Well, I know that this coordinate is x. So this one then would be negative x. But I know that this distance is x and this distance is x. So if I draw my rectangle, this whole thing is 2x. Now this distance right here, this is going to be negative x squared plus 1, because that's the coordinate right here. So whatever x is, you plug it into the function and you get the y value. So now we need to find domain. This is important because it tells us when we're all done which answers work and which ones do not. So if f of x is x squared plus 1, you set that equal to 0. Negative x squared plus 1. And you get x squared equals 1, so x is plus or minus 1. So then the domain is from negative 1 to 1. And then our area of the rectangle is going to be 2x times negative x squared plus 1. So you get negative 2x cubed minus 2x plus 2x, if you want to write it like that. That's going to be helpful for when we take the derivative. So now we know the endpoints of the function. Now let's find our critical points. We find our critical points by taking the area function, which is negative 2x cubed plus 2x, and taking the derivative. A prime of x is equal to negative 6x squared plus 2. You set that equal to 0 and solve. So you get negative 2 equals negative 6x squared. So you get x squared is equal to 1/3. So x is plus or minus radical 1/3. Now let's talk about this. I said earlier that our domain is negative 1 to 1, and I sure hope somebody caught me on that, because can the domain be negative? I know right here I solved, I got plus or minus 1. However, let's think about what we're talking about. An x value about side length. So in fact, we have to exclude the negative. Our domain is then from 0 to 1, because a length can never be negative. Okay? So that allows us to get our two answers of negative radical 1 over 3. Well, the square root of 1 is just 1. And positive 1 over radical 3. So this one we can exclude. So we actually only have one critical point to check. So let's check our endpoints. We have x equals 0 and x equals 1. So the area of 0, well, that's just 0. Because we're going to end up plugging in 0, you just get 0. Let's try 1. You get 2 times 1 times negative 1 squared plus 1. And you get 2 times, oh look at that, 0. And so you get 0. These are probably not the maximum area. Now let's try 1 over radical 3. You're going to get the area of 1 over radical 3 is equal to 2 times 1 over radical 3 times negative 1 over radical 3 squared plus 1. So you get 2 divided by radical 3 times negative 1 over 3 plus 1. 2 over radical 3 times 2/3. So you end up getting 4 over 3 radical 3. Okay, that's a number. It's positive. It works. So this right here is the maximum area. So now all we need to do is figure out the width and the length, and we'll be good to go. So the width of our rectangle is 2x. So it's 2 times 1 over radical 3, which is 2 over radical 3. Our length then is going to be equal to negative 1 over radical 3 squared plus 1. So you get negative 1/3 plus 1, which is 2/3. So now for our summary. The rectangle with a maximum area of 4 divided by 3 radical 3 has length 2/3 and width of 2 divided by radical 3. And there's your answer. Because I didn't put units, you don't have to write the units. And that's it. That's how you optimize a shape underneath a curve.